This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello everyone, welcome to this episode of Software Engineering Radio. This is your host Kanchan Shringi, and today I'm really happy to welcome Dhruba Borthakur to our podcast. We're going to talk about embedding real-time analytics in applications. Dhruba is CTO and co-founder at Rockset. He was the founding engineer of the RocksDB data store at Facebook. Earlier at Yahoo, he was also one of the founding engineers of the Hadoop distributed file system. Dhruba has also been a contributor to the open source Apache Edge-based project. Dhruba previously held various roles at Veritas Software, founded an e-commerce startup called OneReceipt.com, and contributed to the Andrew file system at IBM Transact Labs. You have quite an impressive resume, Dhruba. So happy to have you here and really looking forward to today's conversation. Is there anything you'd like to add to your bio?
No, thank you, Kanchan. Thanks for inviting me. Really appreciate your invitation here. I'm very excited to be talking to you about real-time analytics. Let's
get started.
Yeah.
So before we jump into it, I do want to point out that we have done a few related episodes in the past, and there are about 5 or 6 episodes. We'll have a link to those in our show notes. Include any references that we discovered during our conversation as well, Dhruba. So why don't we start with a very basic question? What is real-time analytics?
Yeah, that's a great question. I have been asked this question many times, and sometimes it's difficult to explain as a definition, but what I can try is to give you examples or define what is real-time analytics. So real-time analytics is typically a way for somebody to look at very fresh data and make decisions based on this data. Take, for example, you are trying to make a prediction or you are trying to understand relationships between different events happening in your system. And you want to do it in real time, in the sense you want to do this decision making as soon as the data gets produced. So this is real-time analytics. It has 2 characteristics usually. It's about the freshness of data and how quickly can you make decisions based on this data. Sometimes people also talk about real-time analytics as analytics that are very customer focused, because if you try to make decisions based on behalf of a customer or a user, these are people who are online, who are waiting for the results to appear. So the queries need to be really fast for these kinds of analytical applications. A very simple example for real-time analytics could be, take, for example, Google Maps. Take, for example, right? You're driving down the highway and there's an accident. Now, your app, in this case, the Google Maps app, have to show you an alternate route. And that has to happen in real time. It cannot be based on traffic data that was created like 10 minutes ago, right? So this is a very simple example of how real-time analytics are kind of built into some of these back-end applications that are becoming more and more prevalent these days.
The 2 things are, of course, someone's waiting for the data. They've asked a question. They want a response right away. But also that the decision, the response has to be based on really fresh data. And you provided a great use case for that.
Yeah, the freshness of data is super important for real-time analytics. There are many other systems that are in the analytical domain that is about making decisions. But a lot of those applications make decisions based on old data. For real-time analytics, the freshness of data is super important for these kind of applications.
So you brought up other applications. So this is a good time. Maybe you can contrast with how traditionally OLAP and OLAP operations are understood.
So if I contrast with traditional analytics, you brought up this term called OLAP and say OLTP, right? So take, for example, OLAP. People refer to OLAP as online kind of analytical processing. So they're online in nature, but again, the data is usually not as fresh as people would like it to be. Most of the applications that are out there, they build cubes, for example, or they build pre-aggregations. They already try to kind of summarize the data in more coarse-grained format so that queries are fast on this data, which basically means that they curate the data, they clean the data, They put it in a queryable form. And after that, when they serve the queries, the data is not changing in nature. So by definition, most of these OLAP systems are there where you take a bunch of data, you process it, and then you start to use it to make decisions. So by definition, it's not real time, because by the time you took this data and made it queryable, you are doing some kind of a batch processing system. This is how traditional analytics happen. These OLAP applications, they typically scan through a lot of data and they make something called cubes. Cube is more like a bucketization software where you
said pre-aggregated.
Correct, exactly. They pre-aggregate in using 9 or n different dimensions. And now because they're pre-aggregated, queries are fast. But the challenge again is that because it's pre-aggregated, it doesn't mean that it has taken any of your fresh data into account. And that's how traditional analytics works.
And the processing takes time, as you mentioned.
Processing takes time. Making the cubes take time. The cubes don't change once you make a cube. Let's say you make a cube every day for 10-minute cubes, right? Now, you can't really backfill data into these 10-minute cubes that you already made. So it makes your analytics not real-time in nature in general. The only way to change this model to make it more real-time is to be able to build a lot more real-time indexes or lots of pointers into this data so you can update things in place so that you can make it more real-time in the future. People have built indexes on this data rather than cubes. Building an index is a great way to kind of make data real-time rather than building a cube, because indexes can be updated as and when new data comes in. But yeah, there is a big difference between how OLAP traditional queries happen and how real-time analytics typically occur in real life.
Is there any relation to the amount of data? Is there, where does big data come in?
Big data is kind of a very ambiguous term these days, right? In 2005, I think big data revolution kind of started, or 2006, around that time. But what has happened right now is that almost all data sets are big data by definition, which basically means that if there's a solution or if you have a system that deals only with small data sets, that is usually something that is not interesting to most people. So now I think the other things that I can add to your question is that big data itself has kind of 2 or 3 different dimensions. One is the velocity of data, which means that how fast is this data coming. One is the size of the data, which means that how big is this data set. And the third one is, what is the variety of data? How much complex is this data? Is it all one format or is it 5 different formats coming in? So for real-time analytics, I think it's super important to be able to process different data formats. It's super important to be able to deal with a high velocity of data. So let's say you might want to pin me down, but I would say that maybe somewhere between a few megabytes per second to a few gigabytes per second could be the velocity of data that's coming in. This is new data produced by events, right? This is your streaming data set that you are capturing by your application, and you want to look at all this data to make decisions. So this is the challenge for real-time analytics. I keep going back to my thinking is that real-time analytics is hard because of these reasons.
3 things stood out for me. Besides being fresh, it is typical that all the data today will be of high velocity, changing, and different variety, a large number of data sources. And then you said streaming. So what is streaming analytics and how does that contrast with real-time analytics?
Yeah, so streaming analytics and real-time analytics are complementary in nature, I think. So when we talk about streaming analytics, we usually refer to the fact that analytical processing is occurring when data is streaming into the system. I said about, let's say, high velocity of data. When all the data is coming into the system, at that time itself, you could afford to do some processing. When new data arrives, it triggers a set of actions that generate insights from that data. This is streaming analytics because it's happening as part of the stream. It's also sometimes called as right-time analytics, where analytics happen when data arrives into the system. These insights, once new data comes into the system, you can generate insights, and those insights can trigger more downstream analytical processing. This is all called streaming analytics. It's like a data waterfall, like water falling from a higher level to a lower level. At every level, when data is flowing downstream, it's processing some analytical decision making. This is all streaming analytics. On the other hand, real-time analytics typically use a combination of both write-time analytics as well as read-time analytics. So you could have some streaming analytics, which is building some write-time aggregations. But if you're talking about just real-time analytics, it also needs a lot of variability in the queries, a lot of complex power in your queries itself, because your queries could be different from point to point. If my application is making a query to the database, my query could be completely different from another person making a query to the same backend source. So essentially, real-time analytics uses a combination of streaming analytics as well as query time analytics to provide the real timeliness of your application. So they're kind of two different complementary things. If you have streaming analytics, it doesn't need to be real time. But if you have real-time analytics, it's usually the case that you need some form of streaming analytics and some form of query analytics built into the system so that you can respond to fresh data quickly at high volume and at large scale. So they're complementary to one another, I would say.
Okay, got it. So streaming is assumed in a sense, and over that you have read-time analytics. So there's still work going on, there's still processing going on. So how real time is this, or is this near real time? So is it minutes, seconds? Can you talk about that?
So again, I think when we talk about real-time analytics, we talk about freshness of data. And I think your question is that how fresh is this data? Is it 1 second freshness or is it 1 day freshness? So that's an answer that depends on the application itself. But in general, when the industry talks about real-time analytics, they're mostly talking about a data latency of, say, a few seconds to a few minutes. So this is why, so let me backtrack and explain the difference between data latency and query latency. Data latency measures how real-time is your data. It is the latency from when the data was produced to the time when it is available to make decisions, right? It's available in your query engine. That's the data latency. And query latency is when you issue a query, how long does it take for the query to come back with results from your backend system? So for real-time analytics, the data latencies usually are a few seconds to maybe a minute or two. Let me give you an example. Let's say you are like in a food delivery use case, right? You have an enterprise that's delivering picking up food from restaurants and delivering it at homes. Now there, maybe let's say the entire distance or the entire delivery cycle is, let's say, 15 minutes, right? For a backend system that can react to changes in delivery, like a delivery person is breaking down or the food is not ready or available. So there, less than a minute should be your data latency, because you need to react, because your entire cycle is just 15 minutes, right? So from pickup to delivery. So there, the data latency could be really small that you need for real-time analytics. But on the other hand, if your logistics system is delivering luggages or goods from one place to another, from the East Coast to the West Coast, you might have only one train that comes every day. So there, your data latency could be maybe minutes or maybe an hour or so as well. The whole point is that real-time analytics essentially reduces the latency of your data. It is, sometimes people also ask me these questions about, are these systems online or offline? That's another way to look at how real-time this data latency can be. And my answer there is that real-time analytics mostly are online systems. They're not offline back-end batch systems. They're systems that if they don't react quickly, then your targets or your audience suffers an outage or suffers a disadvantage, or they suffer bad decisions which are not optimal for your business, or it's not optimal for the users of your system. Yeah, so it's kind of not very clear cut in my mind exactly what the number is, but it's usually seconds to minutes.
So you've given us a couple of examples of use cases. And in that, there was already an action that had to be taken, your Google use case for maps for people to reroute. So essentially, the goal is for people to perform an action, right? Not just being able to get the information, but be able to perform the action, in which case, of course, the user performing the action. But there are other cases where I guess there has to be an automated action also required. Would you be able to provide any such use case?
Most of the real-time analytics systems that we see in real life, they're actually automated in nature. I took the Google Maps example just to give it like a human color. but actually the decision-making process is very much automatic for most other systems. So take, for example, let's say we talk about, like, say, construction logistics delivery company, right? There's an enterprise which is in the business of producing cement and delivering it to construction places where big buildings are being constructed. You'd be actually amazed that there's a strict latency between when the cement is mixed and when it needs to be put on the building. Otherwise, it goes waste. So now what happens is that there is a complex process where at the construction site, there are a lot of sensors, which is figuring out how well is my hydraulic lift working? How fast is it able to do its work? How many steel pipes have I installed till now? Because based on all those sensors is when the cement needs to be mixed in a faraway place. And then the cement is loaded into trucks and delivered to this construction site. Now, this is all could be automatic. This is a very real-time analytics situation where you are getting sensors from many different objects in a construction site that's being fed into a back-end system. And then based on irregularities or anomalies of this process, the cement needs to be mixed at a different time and then loaded into trucks and delivered here. So this is a very automatic process. There's no humans involved. I mean, it's all software. And then here, the data latency is super important for these kind of users, because if they miss deadlines, then the cement goes waste. The driver who drives the truck cement and he gets to the construction site finds out that all this 3 hours of driving has gone waste because now the cement cannot be used at the right place at the right time. So there are lots of industries where the cost of a non-optimized algorithm to deliver their products is super impactful for their products and their business. And this is where real-time analytics is really useful for these kind of use cases. Similarly, I think you might have seen also like a flight trackers or flight paths that are being taken by airlines. There also a lot of it is real-time analytics, because constantly the machines on the ground are actually telling the planes exactly what route exactly to take. I mean, there is a direction that's set in the beginning, but there are so many small changes being made in the route as and when the system and the plane is running. And those are all automatic systems. They're not people making decisions from minute to minute or second to second. These are all software making decisions based on fresh data.
Thank you for those two examples. They certainly make a lot of sense to me. And in both cases, it was clear to see the fact that there is a lot of data. This is big data. The velocity is changing. The sensors are constantly generating data. And certainly the variety, probably many, many different kinds of sensors. So I think it matched all the metrics that you asked us to look out for real-time analytics. And clearly for these, the use case seems obvious. If you don't do this, your flight path is not correctly computed. It could have accidents. In the other case, the cement could go waste as well. So that's clear. But it may not always be the case that you need to have decisions right away. So I'm sure it's based on the use case. So how do people come to a decision that they need real-time analytics? Because I'm sure there are costs associated with this. There must be some cons, because otherwise, why wouldn't you do this all the time? Maybe let's start with talking about the costs involved, and then we can see in what are the things you would ask people to look out for to know that, yes, they do need real-time analytics.
There's definitely a cost to real-time analytics, right? So real-time analytics is a hard problem to solve. That's why most current use cases that people use, they use stale analytics. They said that, okay, I'm going to live with stale analytics where my data is 1 hour old or 1 day old, because I don't have the resources to be able to do real-time analytics. That's how the state of affairs were in the software industry in the last decade or so. But things are changing now. But coming back to your cost, the question of cost is super important. So the cost of real-time analytics is falling actually day by day, not because some new invention has happened, but because more and more people find that this is an important problem to solve. So there are new techniques that are being developed. So the biggest cost of real-time analytics is that first you have to plan for all types of data. This is not easy. So in traditional ways, people will set up 5 different systems to deal with 5 different data sets. And then they have to manage all these data sets, all these 5 different systems by themselves. They might have a relational database. They might have some document database. They might have some other kind of backend systems to deal with this variety of data. So that's a big cost in general for people. The other is essentially operational overhead of real-time analytics. The operational overhead of reacting, like let's say you have a high volume of data coming in and suddenly something is not working. Now all that traffic needs to be rerouted through a different channel so that you don't lose any of that data. You see what I'm saying? So real-time analytics is not just about getting data and processing, but it's about keeping all these big pipes up all the time, 24/7, so that you never lose some pieces of data. Otherwise, your system is going to be a problem. So there are big costs involved in it, but I can also explain how some of the newer technologies are helping people to surmount some of these challenges regarding cost. Take, for example, there are lots of public clouds that people are leveraging to kind of deploy these data systems. So that's one way where there are a lot of automatic processes that help you do fault recovery, right? Like if a machine goes down, there are automatic ways to spin up new machines or new hardware and not have to lose any of the data that's coming in at high volume. Similarly, again, I can go into some more depth about how systems have evolved over from batch to real time and how some software changes have happened to be able to manage all these costs. The costs essentially have come down drastically over the last maybe year or so now, or maybe last 2-3 years. But it's something that people should definitely think about, because the cost is not just about the streaming data, but also the high volume of queries that you need, because most of these real-time analytics are used by other pieces of software. So they need to make queries sometimes at high volume and high QPS. That's definitely one cost. And the last part of the cost is about matching demand. So it's likely that the workload of your system needs to go high during the daytime, and then maybe there's no work for it in the nighttime. Like take, for example, my cement construction company. Most of the time in the night, there is not much work going on in this business because the physical workers are not constructing the buildings that much. So your system has to manage costs by being able to spin down unused resources when not in use and then spin them up back again when daytime starts. Again, this has to be automatic. This is what I mean by there are lots of traditional costs, but a lot of the newer systems that are out there, they try to avoid these costs by building software to be more intelligent.
So my takeaway was really that maintaining the data systems themselves, then absorbing the operational overhead of making sure that the system is operating all the time, matching demand, tuning it so that you are able to react when you do need to react. And what do you do when you don't need to react? Are you ensuring that your systems are well utilized for some other purpose maybe at that time? And public clouds have certainly helped in this area. That was my takeaway from this. So thank you. This is a good introduction to, what is real-time systems, some basic use cases. And we also talked about the costs of it. So taking a step back, let's talk about batch, because I assume that's where people started. Contrasting batch with analytics a little bit more, what did people do earlier? What were the typical components used for batch mode?
Analytics has always been batch for the last maybe 30 or 40 years now, since people invented computers to store data and do analytical processing on it. But if you look at only at, say, big data systems, most of big data started around in 2005 or 2006 or 2000, somewhere around the middle of that decade. And it all started with a paper from Google, which talked about the Google file system. They said that, Google produced a research paper saying that this is how large data sets can be stored in disk systems, right? And using that paper, there was a project that got built in open source. It was called Apache Hadoop project. I was part of that project. And this is a system that essentially let you store a lot of large data sets. But the focus always has been, or at that time was, how can you store terabytes, and petabytes of data into this system? The focus wasn't how quickly can you make decisions. You see, so the design goal of these systems were very different in the last decade. The last decade, the challenge was, how can I store petabytes of data cost effectively and cheaply and not have to drain all my pockets? So this is where Hadoop became very popular. It was one of the first systems that you can store a lot of data. You can make queries. There is something called Hadoop MapReduce, which again is a very scan-based system because these are all batch systems. The focus was queries that can do full scans of your data and produce results and reports. The focus was not on leveraging your most recent data set. The focus was not on low latency queries. The focus was entirely on how can I store petabytes of data and then I can make one gigantic scan of this data and give me results that I'm looking for. So that is how it all started in the beginning. But then another kind of evolution that happened is that SQL systems started to take a little bit of hold in this. In the beginning, Hadoop or any of these big data systems were very much key value stores or like some custom APIs, but then people saw that using SQL is a great way to leverage the data in these systems because SQL is a way that's easily understandable and many developers can adopt it very quickly. You can express very complex computations using very simple SQL statements. So the developer doesn't have to think about a lot of complexity. It just specifies that, hey, this is what I want to do with these two data sets. I want to join this large data set with this data set, and then I want to do some aggregations. And it's up to the software to execute all those commands. So the developer or the application developer really like to use SQL, or the BI analysts. So SQL started to take hold on these systems. And now more and more big data systems or any data systems, I feel like SQL has become kind of the lingua franca of all these applications. Not because SQL is some magic language, it's just because it's a very versatile language. It allows you to do all kinds of operations with the data in a very declarative way. You don't have to write a program or a functional program to specify the steps. You just tell the system that I want to do these things. You figure out how to do it best and give me the results. So this is why SQL has become so popular on some of these big data systems. But it's an evolution, I feel, as far as traditional data systems are concerned. They're very much batch systems and full scan systems. And this is why real-time analytics wasn't really possible on those kind of systems. They were very batch-oriented, and batch-oriented means that you cannot take fresh data into account because you create a batch of data to be processed, and then you keep processing it for the next hour or the next day.
So is HDFs no longer part of the ecosystem for building real-time analytics?
Yeah, that's a good question. So I was the project lead of the Hadoop file system back in the days when it was a very cutting-edge software project. I feel like Hadoop has kind of lost its charm in the last maybe 2-3 years. Back in the days, it was a very powerful system. But now what has happened is that people have started to move to the cloud. And the cloud means, like said, Amazon AWS cloud or Google cloud or Azure or some other cloud systems. And there, these cloud vendors already have an HDFS equivalent system that is pre-installed for you. Like in Amazon, it's called S3. So you can have an object store that scales infinitely. So there is no advantage or there is no differentiator as an enterprise who is using Hadoop to be able to say, hey, I run my own Hadoop, because the cloud vendors run it for you. So HDFS, I think, is losing its charm. Similarly, MapReduce, which is very much a batch system, is not what people are looking for these days, because again, mostly people are thinking about real-time analytics, not batch analytics. So it is changing. Also, if you use Hadoop, you still look at things in a very old-fashioned way. You have to look at capacity planning your Hadoop cluster. You'd have to look at how much CPU you use, how much storage you combine together in the HDFS cluster. Whereas if you use some of these cloud vendor solutions, they're actually just pay as you use service. You don't have to capacity plan any of these things. You don't have to think in advance how much data you're going to use the next day or next month. So people have more or less migrated to a lot of cloud storage systems that are out there. But HDFS or Hadoop is still used by some enterprises. I'll give you one or two examples without naming the people, because I work closely with these enterprises. There is this company which deals with buying and selling used cars. They have a service that allows users to see what others paid for similar cars in their neighborhood or in the local area, and publish this to the dealers of the cars. they store all this data on an on-prem Hadoop file system, right? And they use something called HBase, which is a database, a key value store built on top of Hadoop. But again, this is not a real-time system. This is the difference of those systems. Like, they can look at used car prices of yesterday and earlier, but not like the latest ones. Like, if somebody is making any changes today, they don't get reflected for 24 hours. Similarly, there are some big financial firms that continue to use Hadoop. First of all, they have far more restrictions and regulations, but they do store things like mortgage deeds or loan repayment history, these kind of things on Hadoop, and they run the risk assessment and analysis on Hadoop file system. And these risk numbers, they don't really change from like minute to minute or hour to hour. So it's okay for them to not have these real-time concept for these kind of use cases on the Hadoop backend.
Okay, so the point is that the use case it was built for at that time was quite different, and a change is certainly needed. So moving on to that, like what's new? What have you been working on? Would like to focus on that. I read a little bit about Rockset and I came across the term aggregator leaf tailor architecture. So I do want to ask you about that. But before that, what is Lambda and what are its shortcomings? Why did you have to create something brand new?
So for people who are in the data landscape or people who deal with data systems, software systems, I think the Lambda architecture has become very popular in the last few years. So what the Lambda architecture is that it says that there is a batch pipeline to load data into your system. And then there's also a streaming pipeline into which you load data into your system. So the Lambda architecture says that there are two pipelines to load data into your system. You cannot get rid of any of these because you need real timeliness. It's great to have these two pipelines built into your system. The Lambda architecture, the focus of it is that how can we get good efficiency and good throughput of your system? That's the design goal of the Lambda architecture. So which means that you have, let's say, 100 terabytes of data, which means you have bulk processing pipeline. But then you also have, say, 1 gigabyte of data per second coming in, which means that there's a streaming component to it. And the Lambda architecture very clearly says that this is how you should build a system so that your system is optimized and you get the best value for your money compared to the amount of data that is coming into your system. But you realize that it is not really talking about real-time analytics. It's all talking about efficiency and throughput of your system. Now, based on our discussion, I hope it's getting clear in our minds that real-time analytics is about efficiency, but the real focus is ability to react very quickly to changes in your events.
So it seems similar to your answer to the earlier question on the difference between what is streaming analytics and what is real-time analytics. So beyond just loading the system, which seems to be the focus of the Lambda architecture, you're saying there's to be more optimizations needed for the reading.
Correct. Absolutely. So Lambda doesn't tell you much about how fast can your queries be. How are your queries changing from minute to minute? What is the query volume of your workload? Those are not part of the design of the Lambda architecture.
Okay. So then let's jump into the specific technical accomplishments with the aggregator leaf tailor architecture.
We at Rockset, we use the aggregator leaf tailor architecture. In short, we call it the ALT. So the ALT architecture by itself is not something that suddenly came out of the blue because of a lightning bolt from the sky, right? It is inspired by many of the systems we built when I was at Facebook, some of the backend systems. I'll give an example of where you might be already using ALT architecture system. If you use Facebook, you load the Facebook app and then you see the Facebook feed, right? The data feed, which is about comments, posts, likes from your friends. So that's a data feed that's coming in at actually very high volume because all your friends are posting things or liking pictures. And it's an analytic system, the Facebook newsfeed, because it doesn't show you everything. It does a combination of your best friends that is tries to apply some logic between a ranking between all the feeds that can possibly show in your system, right? And it does relevance matching, sorting, and then shows you the feed from the Facebook app. So this is a real-time feed which is focused on reducing data latency. You don't want to see posts from your comments from your friends which was posted yesterday, right? You want to see them right when your friend posted the comment. So this backend was built using an ALT architecture or ALT-like architecture. So what happens is that the beauty of the ALT architecture is that it is focused on serving low latency queries on large data sets. It has to be efficient and optimized and throughput optimized, just like Lambda, but it has an additional constraint that your queries have to be fast and you should be able to support a large volume of queries if needed. So this is the difference from the use case perspective. This is the difference of an ALT architecture. Now, if I double click on it and I peel off one more layer of the onion, the technical differentiator of the ALT architecture is that it has three components. It has the aggregators, leaf, and the tailor. So the tailor is the component who is basically involved in writing to the system. So when you're sending data into the system, it's the tailors who is actually indexing this data or creating it in a format that is queryable. That's where a lot of work is happening on the tailors. And then the tailor sends it to the leaves, and the leaves are the components that store this data persistently so you don't lose it. So this is kind of your storage system, the leaves. And then the aggregators are part of the query system. So when queries come in, the aggregators are the components that fetch data from the leaves and do whatever processing your SQL query might be telling you to do and then give you results. So there are three separate stages in the ALT architecture. And the reason why this is important is because this is a disaggregated architecture perfectly built for cloud systems. This did not appeal much when you have an on-prem system where your hardware is fixed. The reason it's a disaggregated architecture is that it's very cloud friendly. And I can explain again why. So what happens is that if there's a high volume, if your write rate to your system increases, then you spin up more and more tailors. You don't have to touch the leaves and aggregators because it's just more data is coming in, but the amount of data that you have in your system is constant or the queries are not increasing in nature. So you just need to scale up the tailors. Similarly, when there's no data, you spin down the tailors and you don't have any extra cost for the tailing component, right? Similarly, if your data set increases day over day and month over month, then you need to add more and more leaves. But if your data set is decreasing because of whatever reason, then you can keep shrinking the number of storage nodes and the leaves in this system. And the aggregators, these are actually super exciting because when more queries come, you spin up more aggregators and you serve them at the same low latency that your real-time system needs. But then when there's no more load and people are sleeping or whatever in the nighttime, or maybe it's not Christmas Day, so something else or less load, you can spin down all your aggregators and you have no cost for spinning up. So basically the disaggregated architecture of ALT is cloud friendly and it can give you the lowest cost compared to an on-prem system where you have to provision everything for peak capacity. This ties into your other question you asked me saying, how can you reduce cost for real-time analytics? So ALT architecture is a great way to reduce cost as well because it's disaggregated in nature.
Could you contrast it with Apache Druid, Flink, and Kudu? From my impression, they have been used for similar use cases.
So great question. From an architecture perspective, there are different systems. So like I said, the aggregator, leaf, tailor architecture, because there are three parts of the system. So what has happened is that the three things that are disaggregated in this architecture is the CPU that you need to write data to the system, right? And then the second thing is the amount of storage in your system. And then the CPU that you need to serve queries from your system. There are three different things in this architecture. Whereas take, for example, if you look at Apache Kudu or Druid, there is no clear separation between the compute that you need to write data into the system versus the compute you need to query. They're a shared set of compute servers. So now what will happen is that, that works fine for many use cases, but the challenge for that architecture is that if suddenly you have the high write volume, let's say suddenly some software started to send 100 times more data than it was doing last hour, now your queries will suffer because it's sharing the same amount of CPU or the same set of compute nodes that are used for writing the data as well as querying the data. They're not segregated in nature. So it's because it is shared in nature, which is why similarly, if suddenly there is a high number of queries coming into an existing system, let's say Druid, for example, your new data might get delayed because now it's not as fresh anymore because all the compute is being used to serve all the queries in your system. So this is one big difference from the architecture perspective. Now, you also mentioned about Flink. So Flink is very much a streaming system, which basically means, again, the difference between streaming analytics and real-time analytics. So take, for example, in ALT architecture, you could actually use Flink as well as part of the tailors. You could think about Flink as if the tailors are made of Flink nodes, where things are happening when data is coming into the system, but then you actually store it in the leaves where the actual data storage is. And then the aggregators could still be there to query all the data that your Flink has outputted to the leaves. So Flink more is like a streaming system where you can process data as and when it's coming in. And after you are done processing, you can park it in the leaves, and then the queries can come in through the aggregator. So they're kind of complementary to one another. Flink also could be similar to, say, Spark's streaming use cases, where you can use it more like an ETL tool, where it's a set of transformations that you can do using Flink, and then you can park it in an ALT architecture system, and then you can start queries using the leaves and aggregator. So yeah, I think I've seen people who kind of use that in that the ALT architecture as well as Flink together in one system.
The message that I keep getting is the fact that a lot of these systems were optimized for the storage. And what you're now focusing on is how to make the query better with real-time indexing and how to scale these three components separately so that it's cloud native.
Absolutely. So the focus for the ALT architecture is how can you serve a lot of queries efficiently? How can you make the queries low latency? And how can you make sure that you use only the minimum amount of hardware needed to serve these queries? So there are three things to make these queries efficient. You also mentioned about indexing. So indexing is super useful for us to be able to serve queries in low latency. I mean, indexing is a time-tested way of reducing query latencies. I mean, if you look at a MySQL database or the database that was produced, even anything else, Informix, whatever else was there 40 years back, they all had this thing called indexing. It's just that nobody had actually used indexing on large data sets before. So most of the indexing was for small, like very relational kind of transactional databases. People never actually used indexing for analytical applications. What now people are realizing is that to serve low latency queries on large data sets, you need to index this data. Indexing is the way to reduce latency of queries. So the aggregator leaf tailor architecture lets you do this because there's cost of indexing at the time when data comes in, which is the tailors. And then there's a cost for the queries to be able to use the index as part of the queries, which is done by the aggregator. So yes, the ALT architecture definitely helps the indexing part of things.
Yeah, on the indexing, I did read the term converged indexing. So can you explain what's that?
There are 2 or 3 different types of indexing that people are used to in the software industry are things like a columnar index. Columnar index is an index where all the columns of your records are stored together. Let's say you have a table with 3 fields, right? Name and age and salary. Let's say there are 3 columns in your database. Now, if you keep all the salaries in one place separately from the other 2 fields, if somebody says, hey, give me the average salary of a person, I can just scan through all the salary fields of all the billions of records in my database and give you the average. It's very fast. So columnar storage or columnar index is a traditional way to make scan type of queries fast. That's one type of index that people are used to. Then the other type of index people are used to are something called inverted index. So inverted index is what is essentially used by open source software like Lucene and Elasticsearch. They are used essentially to give you very low latency on point queries. Like suppose you have a query to this table saying that find me the person whose salary is exactly $1,000. Right? So now that'll probably like 3% in your billion or million people database. If you build an inverted index, those queries will come back really fast. It doesn't have to scan the entire table to figure this out. This is the second type of index. And the third type of index are essentially very much like a relational table with a primary key. In this example I gave you, you have the name and the age and the salary. You could have an index with, say, the employee ID of the person. So that's the fourth index. And so now that's how traditionally relational tables are stored, with a primary key. And that's a record or a row-based index that we have, which could be indexed by the employee ID of the person. So if the person is getting hired or leaving the company, you can use the employee ID to find its record and update the fields in the record, right? So the converged indexing is essentially building all these kind of indexes as one thing in the backend. So the application doesn't have to specify what indexes to build. The system automatically builds these indexes. And then based on the query, it tries to use the right index for the right purpose. So typically, a converged index means that you build like an inverted index, you build a columnar index, you build a row index as one thing, and you store it and leverage in your queries. Just to give it a little bit more color, the row index is essentially very much like MySQL or MongoDB indexes that they build by default. The inverted index is very much like what Lucene or Elasticsearch builds by default. And a columnar index is very much like an index that is built by, say, Redshift or Snowflake or Vertica or any other kind of analytical software. So this is the association that a converged index essentially builds indexes from all these different types of backend systems you might be used to and store it in one place.
This obviously affects the rate at which you're able to ingest the data as well. So maybe talk about some of the technical challenges there. Is that what led to the separation and trying to scale them independently?
Yeah. In general, I think people think that building indexes is costly. That's why most databases have a field saying create index on this column. If your record has 500 fields, they don't want to build 500 indexes, because building indexes in general has been a difficult proposition for most users. But at Rockset, what we do is that we do build a converged index for all the fields in your data, because the Rockset technology has tried to make the cost of indexing much lower compared to traditional systems. So it actually makes it economically feasible to build indexes on every field of your data. So now think about the power of the system. You don't need a DBA, first of all, to build an index on whatever fields are there. An index is built on every field. And so now when a query comes in, almost all the queries are fast because the indexes are on every field of your data. You asked me about the challenges of building that index. So the challenges are multifold, but let me tell you how the challenges are addressed in our software. One of the challenges is that we don't use a B tree to store this data. So typically a binary tree or a B tree is how databases store data. So what happens is that the B tree has something called a very high write amplification when you're updating data, because that data gets updated in place. Whereas for building these indexes for converged index for Rockset, what we do is that we use a log structured merge tree instead of a B tree. It's called an LSM engine. So we use an LSM engine called open source RocksDB. So that lets us index a large volume of data at a much better price performance compared to a B tree based database that people are used to earlier. That's one. And the second way we try to address the challenges is that Rockset Converged Index is very much built as a search engine and not like a database. Think about like Google search, right? When you are searching for a term, it's built for low latency. But when you are searching for restaurants in San Francisco, right? Let's say you are searching for that. It's actually hitting a large database and giving you results back. But the database is optimized for latency of query latency, right? Your queries need to be really fast. So Rockset is also built like this. The converged index is basically something, what we call it as a document sharded database, which means that when data comes in or a record comes in, all the fields of the record are indexed on one machine. So a record is not split into multiple servers. Even if your record is very big, it has 500 fields, all the fields are going to be indexed on one machine randomly. And then when a query comes in, the query now has to hit all the machines of your cluster and get results back and give you results back to the user. So it's like kind of uses a scatter gather kind of algorithm to be able to fan out to all possible machines in your cluster and get results back from them. Unlike a traditional database, let's say you are talking about Druid or something else, there when a query comes in, it's going to hit only the machines that have the data because the data is partitioned. Whereas in Rockset or a converged indexing system, we scatter the data among all the machines in a cluster. And so when a query comes in, it has to hit all the machines in a cluster and give you results. So the advantage of that is that it is much more cost effective to build local indices on a document, which is why we adopt this approach. And building all the indexes, you don't basically need like a distributed Paxos or some other algorithm to be able to index data in large volumes, because you have this document sharded scatter gather way of storing all the documents and retrieving results. So those are two primary ways of how we have reduced the cost of indexing on these large streaming databases.
As I hear this, I'm thinking this is blurring the lines for me between OLTP and OLAP. So do you envision this replacing current application workloads, OLTP workloads, as well as search?
Yeah, so that's a good point. So in OLAP, typically people just talk about aggregations and joins, which are basically, like I said, cubing and some other pre-aggregations. But when you are talking about the use cases that most of the real-time analytics or user-facing real-time analytics are used for, they need cubing and OLAPs, but they also need things like search queries. They also need queries like ranking and relevance matching. So these are typically not part of your traditional OLAP characterization that most people are used to. So yeah, probably we need a different kind of a workload, which is basically an OLAP system, but it has far more things associated with it. Some people have started to call it operational analytics kind of thing, where I think OPAP is the name, where online analytics, operational analytical processing, where the real timeliness of the data is super important. So it's not just about cubing. It's not just about aggregations and joins. They have to be there, but you also need searching, and you also need kind of search indexes and relevance ranking and pattern matching to be able to serve all these operational analytical queries that you might need for real-time analytics.
Okay, so one last question for this section before we move on to our last one on embedding real-time analytics. There was a note about schema-less ingestion. Can you explain that?
Yes. So schema-less ingestion falls into the purview of real-time analytics, and let me explain why. So real-time analytics is all about making decisions on your fresh data. So now think about data that is coming in from 5 different sources with 5 different formats, right? One of them is JSON with 5 fields. The other one is coming in from a traditional relational database. The third stream is application logs that are coming in from, say, Kafka or Flink or something else. Now, if there's a way for you to take all this data without having to create a schema, but then make them queryable so that people at the time of query can leverage the schema that is being deciphered by the system automatically, that is called schemaless ingestion. So Rockset, what it does is essentially it allows you to dump semi-structured data from different sources. You don't have to specify a schema at the time of writing this database. So this basically brings out the best of NoSQL database with a SQL database, right? So NoSQL databases, I feel like they became really popular in the last decade because they could ingest data in a free format. So this is schemaless ingestion. On the other hand, software developers, they don't like to create a lot of schema themselves because schemas keep on changing. But they need to use SQL because the SQL is a very complex and powerful language. And prior to Rockset, there wasn't a way to run SQL queries on a NoSQL database. That's why they're called NoSQL databases. So what Rockset does is essentially takes this data, it's a schemaless ingest that's happening, but the system is creating a SQL schema automatically for your application developers. That schema is based on the data that is coming in, and because of the indexing, the system can find out all the different pieces of data, all the different types of data that is in the system, and it actually gives a SQL interface with a well-defined schema to application developers. So now application developers, they feel like, oh, actually it's a SQL system with a great schema. I can inspect the schema. I can call describe table and I can see the schema. But nobody has to create the schema up front. So if your new data that is coming in has new fields, they automatically appear in the schema. This is what I mean by a schemaless ingestion with a strict schema that is used for queries, but not at the time of writing this data.
I will also include your Medium post on the ALT architecture in our show notes, so if interested listeners can go refer to that in detail. So coming to our last section, which is, really the key focus of our podcast today, and we've been building to that, is how to embed real-time analytics in SaaS applications. First of all, what does that even mean, embedding the analytics within the application?
Traditionally, I have seen people use analytics mostly to make their businesses better. How can I make my business process better? There's a lot of analytics which tells you, that lets you do what if situations, right? What if I had done this, then how would my results have been different? That's what traditional analytics is all about. So it has nothing to do with the products that a company is selling. It has more to do with how the business of that enterprise is doing. Now, on the other hand, in the recent timeframes, what we have seen is that a lot of analytics need to be consumed to make the products themselves better. So I gave you the example of the construction company, right? So their product is the ability to deliver cement cost effectively from one place to another. So that's their product. So how can you embed analytics into this product? Another example I'll give you, online gaming. Hundreds of people are playing an online game. You need analytics for things like creating a gaming leaderboard. The leaderboard is who is the best player who can do these 6 different things in the last minute or so. You need real-time analytics because the leaderboarding query is a very complex query. And you don't want to show a leaderboard of yesterday's data because people are actually playing games and they want to see the leaderboard getting refreshed as and when some people are winning and some people are losing. So this is what I mean by embedding analytics into your application. This is a newer area where your company's products are getting directly impacted by analytics. It's very different from traditional analytics, which was more focused on making businesses better.
How does this change the architecture of the application?
Architecture changes because you would see that because they're embedded in products, the volume of queries usually vary a lot. See, if it was a business application, then it will be the CEO or the business analyst in your company who will make a query, let's say, every day or every week. So the pattern is very well defined. Whereas when you build it into your product, I think there are certain demands of the architecture. So the demands of the architecture is that, first of all, the query latencies have to be really low. That's one basic building block for the architecture. And the second one is that the query volume also can change based on how your product is being used by your people. Take, for example, you're running a fitness app on your phone, and suddenly a lot more people are running on the road because it's a Saturday. So now you want to show them an analytical product there saying that who are the top people who are performing today, right? Who's, like, let's say you also want to see how you compared with yesterday's run of your own schedule. Now you need to show them real-time analytics on this, and the volume could change from hour to hour very quickly. So the architecture has to be very much focused on low latency queries on these large data sets, and also the volume of queries could change from time to time or minute to minute. So this is the two basic differences as far as the application is concerned. As far as the data is concerned, also what happens is that the schema of the data keeps on changing constantly, because let's say the fitness app, the application developers, they will try to capture more data from your phone or from your device. Like say next week they're going to ship new features which is also going to catch the temperature of your surroundings where you're running. So now the data stream that is coming into your data set has a new field saying temperature from second to minute to minute. Now your database has to store this additional field with every record. So the data variety also changes because it's the application developer who is controlling what is data getting produced and what is the data that is getting consumed. And the rate of change in your application frequently demands that your data formats are changing or new fields are appearing in your data that you need to process. So you need flexibility in your architecture that can handle multiple data types. Schemaless ingest is a great feature for these kind of use cases. And the rate of change of your application is basically enabled, or if you can support these kind of things in your backend architecture.
So how do you see customers using Rockset now? Is it for augmenting some parts of the stack or replacing some services?
So Rockset by itself is a SQL API on semi-structured data. So in general, people can essentially use it for replacing a lot of their SQL analytical systems that they already have. But this is in theory. This is not what we see in practice. In practice, what we actually see is that people use Rockset for solving real-time analytical needs. Take, for example, this fitness tracker that I gave you examples about, right? So they also have a very good way of upselling products to their users. But it has to be real-time, at that right moment of time that they can upsell a certain kind of product to the user. And it's very real-time in nature. So they use Rockset for this kind of use case. But on the other hand, because Rockset is a SQL system with JDBC APIs, SQL APIs on large data sets, very quickly we see that people also start using it for other use cases just because it's very easy to use. It doesn't have any operational overhead for our users. So what they also see is that now their application developers can move very fast, although they might not need the real-time data to be 1 second. They might be okay with, say, half an hour of data latency. But the fact that it's a schemaless ingest, but the fact that they enable application developers to add more features to their application without having to talk to a database engineer or an ETL engineer or a provisioning or capacity planning concept, they start using Rockset for different things, which are, again, SQL on semi-structured data, but there the data latency might not need to be 1 second. They might be okay with 10-second data latency. They might be okay with 10 minutes of data latency or 15 minutes of data latency, just because it makes them run faster as far as the developers in that company is concerned. So that's what we have traditionally seen for most of our users.
What about the folks building the SaaS applications? So do the developers building it need to now gain some additional skills?
For Rockset, our focus always has been to empower developers, application developers, to leverage the power of all the insights or intelligence that is part of all the data that they're collecting. So most of the time, the application developers who use Rockset, they don't really need to have a data team or a data engineering team to handle all the data needs. They typically start off with making SQL queries over REST. So Rockset is essentially a SQL query engine. So they dump a lot of JSON or CSV or XML data into Rockset. It could be dumped at one time, or the application developer can also tell Rockset that, oh, my data is all in S3, so please suck it in from there. Or my data is in Kafka, so keep continuously tailing. And the thing that they have to learn is how to make a SQL query over REST. So this is one option for most of our application developers. We also have a Python SDK and a Java SDK, where if you know just Python, you could use Python constructs to make queries that automatically get generated. But the even more interesting thing is that, let's say one application developer generates a SQL query and iterates using the SQL query and then finds out that this is the real SQL query to be made. He can actually park the SQL query as something called a query lambda. So Rockset has this concept of a query lambda, which is basically a SQL query that can be stored in the backend with obviously parameterized SQL query. And what it exposes is a REST API that you can hit from any machine or any browser. So you can just hit a REST API. It's no SQL on your client side anymore. The client just hits a query lambda with a query lambda ID. And in the backend, this SQL query is executed and returned back to the application. So we have seen that many people starts to use Rockset as a developer API because not everybody needs to know SQL. If one developer knows SQL and he parks it as a Query Lambda. Now all other developers in his company starts to use that Query Lambda. You can actually use it from any language now because it's just a REST endpoint. It is no SQL thing, or it doesn't need to link in any Rockset SDKs or anything at all. So the developer adoption is pretty minimal. The barrier to adoption is very minimal for a new developer. He doesn't have to learn some new things that are Rockset specific.
Are you tracking any technical challenges that you haven't solved yet, but you have encountered with working with customers?
Absolutely. So typically, customers in different verticals have different requirements. Take, for example, in the healthcare industry, there are certain rules and regulations that are mandated by the government. Like take, for example, in the healthcare industry, there's something called HIPAA regulation. So we are working to making sure that Rockset is HIPAA compliant. But on the other hand, we have ways to be able to mask certain fields of your data so that if somebody has health data and they still want to use Rockset today, they could mask out certain fields of your data so that Rockset doesn't get to know about any of those. Let's say you have some PII data that customer cannot share with Rockset. They can very easily mask it. They can hash it to a certain value. So we have tools to be able to ensure that our customers are adhering to the regulations that they need to. Similarly, say for financial companies, they might have some other sets of requirements that Rockset might not meet, especially related to the security of the data, essentially, right? You can talk about it as SOC 2 compliant, SOC 2 compliance. So we are working on some of those. Some of those are needed to put more sensitive data into Rockset, and we will have all those compliances mostly done in another 2-3 months or so, or maybe a month or so from now. That's one area. The second area of challenges that as a cloud service, and not just specific to Rockset, but any other cloud service, is the ability to give our developers, people who use Rockset, those developers, the ability to debug bugs in their code by themselves, right? So we are building tools and processes so that we can help them debug bugs in their code quickly and easily. That's basically one way for us to make sure that people can run at full speed when they're using Rockset. Some of these are difficult to solve because the variety of problems are quite big.
Thanks for all that, Dhruba. So my takeaway from this section really was the fact that embedding into the SaaS apps is really helping make the products themselves better, in real time, reacting quickly, handling much higher query volumes, many more data types. And as we had talked about earlier in the very first section, this does introduce operational overhead. There's additional things the SaaS developers have to account for, to also build the workflows to react to this, and also to match the demands.
Yeah, that's a great summary. All these things are important. All these things have to fit in place and complement one another to be able to embed analytics into your application.
So let's start to wrap up now. I hope we covered a lot of ground and at least the key things that you were hoping to cover. Is there anything that we missed that you would like to talk about?
For real-time analytics, operational complexity is definitely something that is top of mind for most people. Not because it is hard, but because even in earlier times, people could actually do some of these real-time analytics if they cobbled together 5 different software solutions and they hire 5 people to be able to do real-time analytics. But this is the real differentiator, I think, is that people are seeing more and more solutions in the market to be able to do real-time analytics as a canned solution. Rockset is definitely one of the primary ones there, where you can just point and click different data sources, and you can think about data as an API rather than thinking of data as having gravity and like trying to do a lot of heavyweight lifting. So if there are tools that people can use that can make them use data as a real simple API, they don't have to think about the complexities of queries or scaling up and down or fault tolerance or whatever else. That's a great enabler, I feel, for making these embedded real-time analytics solutions super useful and adopted by lots of developers.
Thank you. How can people contact you?
Please go to rockset.com. So Rockset is a hosted service, which means that as a user, you don't have to install anything. You go to rockset.com, click and sign up for an account. And within 5 minutes, you'll be able to use and try connecting your data set to Rockset and making queries. Sometimes if you want to know more about the backend, instead of trying Rockset as a service, you could also just click on the demo request, or you can just send me email and we can definitely help you answer your questions and see how we can help in setting up your system so you can use it.
Thank you so much, Dhruba. This was a very, very interesting session for me. I hope our listeners enjoyed it and learned from it as well. Thanks a lot for coming.
Hey, thank you. Thanks, Kanchan. I really enjoyed the discussion with you. Thank you.
This is Kanchan Shringi for Software Engineering Radio. Thanks for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.